Physicists have been captivated by black holes for an extended period, a phenomenon that has intrigued scientists for over a century. These enormous entities, which challenge our understanding of gravity, remain mostly unseen. A two-dimensional black hole, 4 million times heavier than the Sun, is extremely powerful. But thanks to decades of research, our knowledge has transformed from almost nothing to uncovering more details, sometimes in unexpected ways. A recent breakthrough occurred when researchers, including those at the Kaku Institute, announced that they were able to view the inside of a black hole. This new data has revealed aspects of the universe that had previously been missed. Let's delve deeper into black holes and explore the secrets they may hold. Space is vast and awe-inspiring, but before diving into recent revelations, it's important to comprehend the foundations of black holes. While many people are familiar with the concept of black holes, significant lapses in our understanding still remain. The theoretical possibility of a black hole emerged in 1916 when Albert Einstein introduced his general theory of relativity, which suggested such objects may exist. Black holes continued to be a matter of speculation until the 1960s, when scientists made their first observation, solid evidence that pointed to their existence. During the investigation of the binary star system Cygnus X1, astronomers discovered an unusually bright blue star emitting X-rays. This star was not a typical celestial body, it was orbiting a mysterious massive object. Upon further investigation, it became clear that the X-rays weren't just floating in space, they were being drawn in that direction, confirming the presence of a black hole. This discovery was a major milestone, proving that black holes were not just theoretical ideas but tangible phenomena. The importance of this finding cannot be overstated, as it meant that an entirely new category of objects existed in space, demanding urgent and careful study. Researchers worldwide then focused their attention on black holes with renewed interest. The first confirmed black hole, Cygnus X1, can be found 6,000 light-years away in the Cygnus constellation. It is much brighter than our Sun and has an enormous pull on Earth, so strong that even light cannot escape it. This is why it is referred to as a black hole. The nature of a black hole is both fascinating and intimidating. It indicates a region in space where the gravitational force is so mighty that nothing, not even light, is able to escape its pull. Anything that comes too close to a black hole is inevitably sucked in and lost forever. This threat makes studying black holes both compelling and crucial. But does this mean we're in immediate danger from them? Despite the nearest black hole being about 500 light-years away, this distance still raises questions about potential dangers. However, the actual scale of black holes is only just beginning to be understood. Following the discovery of Cygnus X1, astronomers began searching for more black holes. It is currently believed that there may be up to 100 million black holes in the Milky Way galaxy alone. Identifying them remains a challenging task, but estimates imply that millions are contained within our galaxy, demonstrating the significance of studying these enigmatic objects. The primary concern with black holes is their immense gravitational force. This pull is so strong that it draws in everything, including light. At its center lies the singularity, where all the matter that falls into the black hole is pressed into an infinitely dense point. In simpler terms, black holes act as cosmic vacuum cleaners, pulling in everything within their reach. If a person were to fall into a black hole, they would be compressed and stretched until reduced to a singularity. This process is extremely slow, meaning the person would meet their end long before reaching the final, irreversible stage. Despite the apparent danger, black holes are so widespread that they cannot be disregarded. Even though the closest is far away, the sheer number of them in our galaxy makes them a critical subject for scientific study. In 2019, scientists reached a historic accomplishment by securing the first clear image of a black hole, the supermassive black hole at the center of the M87 galaxy. This photograph was taken over several nights, and each exposure provided more insights. The data was painstakingly compiled to create a clearer image. The most remarkable finding was that a black hole isn't merely a singular void in space. It consists of 3 distinct layers. 1. The event horizon, the point at which nothing can return. Once an object crosses this boundary, it will always gravitate inward. 2. The sphere of photons, a region where light is trapped in orbit. Any light that enters is caught in the black hole's gravitational grasp and cannot escape. 3. The singularity, a point where matter is compressed into an infinitely dense space, creating a region where the known laws of physics break down. This breakdown is one of the many reasons studying black holes is both extremely difficult and captivating. What's even more fascinating is that each black hole acts differently. While they share a similar basic structure, each one operates in a unique way. Unlike other celestial objects that we can study directly, black hole examination is only indirect. Scientists rely on observing the radiation emitted by black holes and the surrounding gas and dust. Sending a probe into a black hole is impossible, as anything that crosses the event horizon is drawn toward the singularity, where it would be crushed. This limitation forces researchers to rely on two-dimensional models to study these three-dimensional objects. Black holes also come in various shapes and sizes, adding another layer of complexity. Researchers have proposed several theories to explain how black holes form. One widely accepted idea is that they come from collapsing stars. When a star runs out of fuel, it can no longer generate the energy needed to counterbalance the force of gravity, causing it to implode. If the star is massive enough, this collapse continues until it becomes a singularity. NASA researchers have concentrated on a particularly potent galaxy, M87, where they observed a massive hydrogen gas whirlpool rotating at an amazing speed of 1.2 million meters per second. Despite the extreme forces at play, the gas did not disperse, leading researchers to conclude that a massive object at the galaxy's center must be holding it all together. This object proved to be a black hole with a mass billions of times that of the Sun. In 1963, Roy Kerr, a New Zealand mathematician, used Einstein's equations to model rotating black holes. Kerr's theory suggested that rather than collapsing into a single point, a rotating black hole could form a ring-shaped disk of accretion. This disk would rotate so quickly that its outward forces could counterbalance the gravitational collapse. Kerr's work also introduced the concept of the Einstein-Rosen bridge, or wormhole. A wormhole is an imagined tunnel connecting two distant points in space and time. The idea of wormholes, and possibly even parallel universes, has intrigued scientists for years. If black holes are connected to wormholes, they could provide shortcuts via spacetime, allowing travel between far-off regions of the universe or even different points in time. However, even if wormholes exist, it is unlikely we would be able to use them for travel in the near future. This radiation could gradually cause the black hole to lose mass and, eventually, evaporate completely over incredibly long periods of time. This revelation was revolutionary because it suggested that black holes are not eternal, they can shrink and vanish, leaving behind no trace. Hawking radiation bridges the gap between quantum mechanics and general relativity, showing that quantum effects do play a role in the behavior of black holes. It also challenges the long-held belief that nothing can escape a black hole. Even though the radiation is incredibly faint and virtually impossible to detect with current instruments, the theoretical implications are profound. One key consequence of Hawking radiation is the black hole information paradox. According to quantum mechanics, information about a physical system can never be lost. But if a black hole completely evaporates, where does the information about the matter that fell into it go? Does it disappear forever, violating quantum law? Or is it somehow encoded in the Hawking radiation? This paradox has sparked decades of debate among physicists and remains one of the biggest unsolved problems in theoretical physics. Various solutions have been proposed, including the idea that information is preserved in subtle changes to the radiation or is stored on the event horizon in what is known as the holographic principle. The holographic principle suggests that all the information contained in a three-dimensional volume of space can be represented by a two-dimensional surface, similar to how a hologram contains a 3D image on a flat plane. Applied to black holes, this idea implies that everything that falls into a black hole is somehow encoded on its surface, not lost within it. This theory has far-reaching implications, not just for black holes, but for understanding the nature of the entire universe. It points to the possibility that the universe itself might be a kind of hologram, with the true physics taking place on a more fundamental, lower-dimensional layer. Modern tools like gravitational wave detectors and more powerful telescopes are helping scientists gather new data on black holes. The first detection of gravitational waves by LIGO in 2015, caused by the collision of two black holes, confirmed yet another of Einstein's predictions and gave researchers a new way to observe cosmic events. As more black hole mergers are observed, scientists gain insight into their properties, their masses, spins, and frequencies of occurrence. Each new detection brings us closer to understanding their origins, evolution, and potential connection to other fundamental structures in the universe. In the coming years, missions like the James Webb Space Telescope and projects like the Event Horizon Telescope will continue to refine our understanding of these mysterious objects. With improved resolution and expanded data, researchers hope to unlock even more secrets, perhaps even resolving the paradoxes that have long eluded explanation. Ultimately, black holes are not just cosmic anomalies, they are windows into the deepest laws of nature. They challenge our assumptions about space, time, matter, and information. And as we continue to explore them, they may very well reveal truths about the universe that we've only begun to imagine. Black holes lose mass over time, eventually resulting in their loss. Although Hawking radiation is difficult to detect because of its fragile nature, it provides useful information about the behavior and function of black holes. Black holes also play a role in the universe as unique laboratories for studying the interaction between quantum gravity mechanics. The extreme conditions near singularities of black holes are where both gravitational forces and quantum effects become relevant, making them an essential part of research for physicists seeking to create a quantum gravity theory. Black hole research may also provide clues about the origins of the universe. There are some hypotheses that the conditions close to a black hole may provide insights into the birth of spacetime itself. This may also be the case if wormholes do exist, and they may offer a mechanism for exploring extensive areas of space and time, making new possibilities possible for traveling across galaxies. Despite these ideas remaining speculative, they continue to motivate researchers to investigate the most fundamental inquiries regarding the nature of our universe. Black holes have sparked a profound fascination among researchers, and their research has advanced significantly over time. These enigmatic cosmic entities defy many of our conventional understandings of physics, particularly gravity. The fact that they remain nearly invisible makes them even more intriguing, and scientists continue to investigate their mysteries with intense curiosity. As our technological and theoretical knowledge improves, our comprehension of black holes becomes deeper and more complex. It's clear that black holes are not just fascinating relics of space, but also serve as crucial pieces of the cosmic puzzle that might help unlock the mysteries of the universe. As we move forward in our understanding, black holes remain one of the most fascinating and intricate topics in astrophysics, and their capacity to bend and warp spacetime itself gives them a remarkable position in the research of cosmology. As we delve deeper into their secrets, we inch closer to understanding the fundamental mechanics of the universe, including the very nature of spacetime and matter. The study of black holes offers insight into how quantum mechanics interacts with gravitational forces, opening new avenues of research that could one day provide answers to some of the deepest questions about the fabric of the cosmos. One of the most significant difficulties that persist for scientists is reconciling the differences in theory between general relativity, which talks about large-scale gravity behavior, and quantum mechanics, which governs the subatomic world. Black holes, with their extreme conditions, provide a natural laboratory for studying these forces together. They are one of the few places in the universe where the effects of both quantum mechanics and gravity become observable in ways that are difficult to replicate in a terrestrial environment. This duality makes black holes especially useful to researchers who are working to develop a unified physics theory that can encompass both of these fundamental forces. The efforts to understand black holes have led to several groundbreaking discoveries. One of the most notable is the finding of gravitational waves. These ripples in spacetime, first predicted by Einstein in the early 20th century, are brought on by the speed of enormous objects, like the collision and merger of black holes. The observation of these waves, first confirmed in 2015, marked a new era in astrophysics, allowing researchers to investigate cosmic events that were previously beyond the reach of traditional observation methods. Astronomy of gravitational waves has provided us with new ways to observe the universe and provided new perspectives on the way black holes act and their role in the universe. Despite the progress made in the study of black holes, there is still much to learn. As technology advances, so too does our ability to explore the universe in new and more profound ways. The creation of stronger telescopes on Earth and elsewhere in space has expanded our ability to observe distant black holes, revealing new details about their structure and behavior. In addition to the growth of sophisticated computer models, scientists now have the ability to model the complex dynamics of black holes and their environments with unprecedented precision. These instruments will continue to enhance our understanding of these cosmic giants and how they affect the universe. Looking to the future, the continued study of black holes is expected to yield even more astonishing revelations. As we refine our techniques for observation and push the boundaries of theoretical physics, we may investigate brand new facets of black holes that challenge even our most established ideas about the nature of reality. The possibility of discovering new types of black holes, understanding their role in galaxy formation, and exploring the relationship between the fundamental structure of spacetime and black holes are just a few of the exciting avenues of research that lie ahead. Moreover, the study of black holes is likely to have far-reaching implications for other fields of science. By understanding the extreme conditions near a black hole singularity, we may gain insights into the way that energy and matter behave under conditions that would not be possible to replicate otherwise. This could have applications not only in astrophysics but also in fields like materials science, quantum computing, and even new technologies being developed. In addition to the practical scientific advancements, the exploration of black holes captures the attention of the imagination of people worldwide. The mystery of what lies beyond the event horizon, the ultimate fate of anything that crosses it, and the strange, often paradoxical nature of these objects continue to inspire a sense of wonder and curiosity. For many, the concept of black holes evokes images of cosmic adventure that lead to more philosophical inquiries into the nature of existence, time, and the universe itself. As we continue to explore black holes, we are reminded that our understanding of the universe is far from complete. These enigmatic objects challenge our most fundamental concepts of physics and provide a window into the most fundamental aspects of the cosmos. The journey to unlock their secrets is a long one, but each discovery brings us closer to understanding the fundamental forces that ultimately shape the universe. Black holes are not merely astronomical oddities, but rather key players in the cosmic dance of the universe. They hold the potential to answer some of the most profound questions about space-time and the nature of reality. While we have made incredible progress, black holes remain a fascinating mystery that persists and encourages research and creativity from researchers and non-researchers alike. The ongoing study of these mysterious entities will continue to produce novel and surprising insights that provide us with a more in-depth comprehension of the cosmos and our place within it. The continued exploration of black holes will undoubtedly push the boundaries of both our technological capabilities and our understanding of the universe. As we develop more advanced tools and methods, the mysteries that black holes present will likely reveal even more about the fundamental nature of reality. Whether it's through the discovery of new types of black holes, or through breakthroughs in our understanding of how they shape the fabric of spacetime, the journey to unlock the secrets of these cosmic giants is far from over. Furthermore, the intersection of black hole research with other fields such as quantum mechanics, string theory, and even the study of dark matter could lead to interdisciplinary breakthroughs that transform how we perceive the universe. The application of quantum principles to the study of black holes might hold the key to resolving some of the most perplexing questions in physics, such as the nature of dark energy and the unification of the fundamental forces. As we probe deeper into the unknown, the search for answers will inevitably lead to more questions, but that is the very nature of scientific discovery. Each answer brings us closer to understanding the universe's most fundamental laws, while each new question deepens the mystery. It is this perpetual cycle of inquiry and discovery that drives scientists to continue their quest for knowledge, and black holes, as some of the most mysterious and extreme objects in the cosmos, are bound to remain at the forefront of these efforts. Ultimately, the study of black holes is not just about understanding these enigmatic entities themselves, but also about gaining insight into the very fabric of the universe. What happens inside a black hole, at the event horizon, or within the singularity, may hold the key to unraveling the mysteries of space, time, and the very nature of reality itself. The ongoing fascination with these cosmic wonders serves as a reminder of how much there is still to learn, and how much more awaits discovery in the vast and largely unexplored frontier of space. As we continue to make advances in both theory and observation, we may find that black holes are not just distant and mysterious objects in space, but rather integral pieces of the cosmic puzzle that offer us a deeper understanding of the universe and our place within it. Whether through the development of new technologies, the refinement of existing theories, or the pursuit of groundbreaking discoveries, the future of black hole research promises to be as profound and exciting as the mysteries themselves.